everyone, and welcome to section 10.1 on sequences. This is Jesse Smith from Maryville College. In this section, we're going to get an introduction to what sequences are, learn about a few different types of key sequences, learn how to write a formula for a sequence, and if I give you a formula for a sequence, how can you list the terms for the sequence, and then finally we're going to wrap up by talking about the convergence of a sequence. In reference to convergence of a sequence, these two notations mean exactly the same thing. They both mean the limit as k goes to infinity. This second notation is simply to save space on the slides. So first of all, what is a sequence? A sequence is an unending list of numbers. Every value in a sequence is called a term of the sequence. The very first number in the sequence is called the first term. The 10th number in the sequence is called the 10th term. I have 8 examples listed on the screen of different sequences. The first sequence is just the natural numbers. 1, 2, 3, 4, 5, 6, 7, 8, and so forth forever. There is a 1000th term in this sequence. That would be 1000 in this sequence. There's a billionth term in this sequence. That would be the number 1 billion. The second sequence here is a little bit more interesting. In this sequence, we start with the number 2. The second term of the sequence is 4. Then the third term of the sequence is 8. The fourth term is 16. The fifth term is 32, and so forth. 64, then 128. Forever. This next sequence, the first term is 1, then it's 1 again. So an interesting thing here to note is that in a sequence, terms can repeat. 2, 3, 5, 8, 13, 21, forever. 1 and 2, you could probably write a formula for the kth term in each sequence. The kth term in this sequence, if I'm starting with k equals 1, so this is the first term, second term, third term, so forth, the formula for this sequence would just be k. While the formula for this sequence, well, it's doubling every time, and if you know anything about powers of 2, you'd quickly recognize that this is simply powers of 2. 2 to the 1, 2 squared, 2 cubed, 2 to the 4th, etc. So the formula for these terms would be 2 to the k. Finding a formula for this sequence is not as easy, but there is a pattern. For instance, 2 is simply the sum of the previous 2. 3 is the sum of these two numbers. 5 is the sum of these two numbers. 8 is the sum of 3 and 5. 13 is the sum of 5 and 8. So what would the next term in the sequence be? It would simply be 13 plus 21. The fourth sequence here, we have 2, 6, 18, 54. Any guesses what the next term in the sequence would be? Well, it looks like I'm tripling every time. This is 3 times, well, wait a minute, this is just 2, and then it's 2 times 3, and then this is 6 times 3, and this is 18 times 3. So this next term would probably be 54 times 3. The dots at the end of the sequences are ellipses, and they simply indicate that this goes on forever, following possibly a similar pattern. Number 5 is just the sequence of 1 and -1 alternating back and forth. Again, terms can repeat. Here the first term and the third term are the same, as well as the fifth term. But in between each of these, it becomes -1, and it just alternate or flips back and forth. 1, then -1, then 1, then -1, then 1, then -1, and so forth. Sequence 6 is pretty boring. It is just the sequence. Listen for it. It's very complicated. 7, 7, 7, 7, 7, 7, 7, forever. The first term is 7, the 10th term is 7, the 3 billionth term is 7. If I had to write a formula for this, where k is the term that I'm at in the sequence, so when k is 1, I get 7. When k is 5, I get 7. When k is a billion, I get 7. What would that formula be? It would just be 7. For any k, the term is just 7. 6 is what we call a constant sequence. because it's a constant value throughout. Example 7 here, there doesn't appear to be a formula or a pattern to this sequence. This is an example to show you that sequences don't have to follow a set formula. This is just a random collection of numbers. I just typed in random values. I have no idea what the next term in the sequence is. There's no relationship between these. It's just random digits. In all of my examples, I've used whole numbers for the terms in the sequences, but they can be fractions. They can also be irrational numbers like pi, square root of 2. Here in the 8th sequence, my first term is negative 1.5. Then my second term is 3. My third term is negative 6. My fourth term is 12. There is a pattern here. Every time it looks like I'm doubling, but I'm also switching back and forth between positive and negative. So I would bet that the next term would be negative. In fact, negative 24, double the last term. We can denote a sequence in a variety of different ways. One way is to denote it this way with a curly bracket at the beginning. A sub k, and this will be replaced by a formula in terms of k. So a function of k, curly bracket. In the bottom here, where your k starts at, so this is telling the very first value your k begins at. Most of the time we will start sequences at 1, but we could start a sequence at 0 or at negative 5 at a different counter, and we'll always go up to infinity. Because of that, that is often left off. And again, k could start at something other than 1. That's not something we really need to stress about, but note you could start a sequence at the 0th term and then go to the first term, and the first term and then the second term, third term, and so forth. You could start a sequence out at k equals negative 3, in which case you talk about the negative third term as technically the first term. Then this negative second term, the negative first term, the 0th term, the first term, the second term, the third term forever, etc. If we're starting a sequence out at k equals 1, we know we're going on and on forever. We'll often just give the formula a sub k. Again, this will be a function of k, and no indication of the starting point or the ending point, because we're going to assume that we know we're starting at a k equals 1 and going up to infinity. So 2 examples at the bottom here. The first one is 1, 2, 3, 4, 5 forever. That formula would just be the formula k. When I plug in k equals 1, I get the first term in the sequence. When I plug the k equals 2 into that, I get the second term in the sequence, and so forth forever. For number 2, it's 2, 4, 8, 16, 32, 64, 128, and so forth. I could denote that by the formula 2 to the k. 2 to the exponent k. So when k is 1, I would get 2 to the 1, which is the first term. When k is 2, I get 2 squared, which is 4. When k is 3, I get 2 cubed, which is 8. When k is 4, I get 2 to the 4th, which is 16. And so forth. I will go through and get the entire sequence. If I let k start at 1 and tick slowly up one at a time to infinity, I would get that entire sequence or infinite list of numbers. So here's the solutions that I just mentioned there. I can write them with the curly brackets, or I can omit them. Since I know that I'm starting at 1 and going to infinity, I can just omit the curly brackets as well as the beginning subscript and the ending subscript. I want you to take just a minute and practice to see if you can go from a sequence written out in terms of the first sequence, second term of the sequence, third term, etc., as denoted in the examples 1 through 4 on the screen, and come up with a formula in terms of k, where when you plug in k equals 1, you get the first term of the sequence. When you plug in k equals 2, you get the second term of the sequence. When you plug in k equals 3, you get the third term of the sequence, and so forth. So for example, on number 1, if I want to find a formula for number 1, I want to find a formula involving k, so that when k is 1, I plug 1 into the formula, and the answer is 10. When I plug in 2, it will give me the second term. It will work out to be 20. When I plug in 3, I'll plug in 3 into that formula that we find, and the answer should work out to be 30, the third term in the sequence. And so forth for every term in this sequence. I want you to take just a few minutes and see if you can't find a formula for each of these 4 sequences, 1 through 4. There is no magic shortcut here to finding these formulas. It simply involves some trial and error. The first thing I would advise you to do is to figure out the pattern involved in each sequence. See if you can figure out the next couple of terms in each sequence 1 through 4. Once you have that, you then know a little bit more about the sequence. See if you can't then deduce, by trial and error, a formula in terms of K that will give you each of the 4 sequences listed on the screen. So pause the video, take about 5 minutes, give that a go, and then restart the video, and we'll see how your solutions compare to mine. Alright, here are my 4 solutions. For number 1, the very first thing I noticed is that everything is a multiple of 10. The first term is 10. Then the second term is 20, which is 2 times 10. Then the third term is 3 times 10, etc. Well, a formula that would do that for me would be simply 10 times k. I hope you can see that when you let k be 1, you get the first term. When you let k be 2, you get the second term, and so forth. Number 2 is a little bit trickier. But if I look at the pattern involved, I notice that every time I'm multiplying by 3, 2 times 3 is 6, 6 times 3 is 18, 18 times 3 is 54. I could figure out the next number, it would be 3 times 54. So I'm multiplying by powers of 3. I'm multiplying by 3's, which means I'm multiplying really by powers of 3, because when you multiply by several copies of 3, you get a power of 3. And I'm starting out at 2. At the very beginning, that doesn't have anything to do with 3. There's no 3 being multiplied at all there. That's weird. But I could do that by multiplying by 3 to the 0. If I did 2 times 3 to the 0, I would get 2. And this is 2 times 3 to the 1. And this is 2 times 3 squared. And then I multiply by another 3, and that will be 3 cubed. So when k is 1, if I plug 1 into this formula, I get 3 to the 0, which is 1, and I get 2 times 1, which is 2. It worked. When I plug in 2, I get 3 to the... When I plug in 2, I get 3 to the 1, which is 3. 2 times 3 is 6. It worked. When I plug in k equals 3, I better get 18. 3 minus 1 is 2. 3 to the 2 is 9. 9 times 2 is 18. It appears to be working. It will also work when I plug in k equals 4. The benefit in having these formulas compared to this notation is that now I can quickly figure out what the 100th term or the 1000th term of each of these sequences is simply by plugging in those values for k. If I wanted to find the 100th term of this sequence, plug in k equals 100. When I find the 100th term of this sequence, plug in k equals to 100. And the number pops out. The third sequence is alternating back and forth between -1 and +1. So let's see, I could do -1 and then multiply by -1 to get 1, and then multiply by -1 again to get -1. So I could just multiply by -1s. If I follow my thought process for 2, I could simply do -1 to the k. Let me make sure this works. -1 to the 1, plugging in k equals 1, will give me the first term, -1. When I plug in 2, I get -1 squared, which is -1 times -1, which is +1. I get the second term in the sequence. Likewise, when I plug 3 in here, it'll work out to be -1, and the formula appears to work. If you see negatives and positives switching back and forth, most of the times you will have something like this in your problem. Finally, 4, it looks like I'm starting at 7 and I'm simply going up by 1 each time. So if I start out with k equals 1, how could I get 7? Well, I could just do 6 plus 1. That'll give me 7. This is a 6 plus 2. That'll be 8. 6 plus 3, that's 9. The formula 6 plus k will work. There are other possible formulas, different algebraic manipulations you can do to these to get different equations that will also yield you the same sequence. If you got a different formula than I have, and you're convinced that it works, and you want to compare it to mine, please send me an email and we can look at your equation and see if it will actually work to give you the sequence at hand. On the other side of the coin, you could be given a formula for a sequence and then asked to actually write out the terms of the sequence. So here, you're given the formula a sub k is equal to negative 1 to the k times this algebraic expression, and we're asked to find the first four terms of this sequence, which means compute a1, the first term, a2, the second term, a3, and a4. I've done that here simply by plugging in k equals the different values into the expression. So when I want to find a1, everywhere there's a k I put 1, I work it out, I get negative 0.5. When I want to find the second term, I make all the k's 2, work it out, I get 0.4 repeating. Likewise, I can find the third term by plugging in k equals 3, the fourth term by plugging in 4, etc. You can get these calculations really quickly in any spreadsheet software like Excel. I would like to show that to you now. So I'm going to exit out of my presentation for just a minute, and I'm going to pull up Excel. And I have an example here already, the same example that was on the screen. Let me blow this up and zoom in a little bit. And I'm going to start a new sheet, which is what you would have if you just opened up Excel. And in this column, I'm going to put my k. So when k is 1, I want to know the first term. I want it to appear in this blank. When k is 2, I want the formula to work out and show me what the second term is in this blank. So here I'm just going to put in this column what my terms are. So let's say the problem at hand was as given in the presentation, which was negative 1 to the k times k squared, all divided by k cubed plus 1. So I'm going to write equal here to actually evaluate a number and put it into this cell. Do parentheses negative 1 to the power. I'm going to use the caret to do the power. When I want to use a k value, actually click on the cell containing the k value, and it puts that variable into the formula spreadsheet. And I want to multiply it by a big fraction. I'm going to put that entire fraction in parentheses. The top of it was k squared. So I'm going to do this number squared divided by the entire bottom was k, that number, cubed plus 1. Close off my parentheses for the denominator. Close off my parentheses for the fraction that I'm multiplying by negative 1 to the k by, and hit enter, and it gives me the number that I got for the first term. If I want this formula to continue down here, I can simply drag this down and it will evaluate that same expression using k equals 2. Excel's pretty smart. If I type 3 here and hit enter, or 4, it's not going to automatically update. Sometimes it does, sometimes it doesn't. But if I double click on that bold little corner, I go back, see that little green dot? If I double click there, it continues the formula down. It gives me the third evaluation, the fourth evaluation. So if I type 10 here, that's when I said Excel is sometimes smart. It knew that I wanted to continue doing that formula below, so it went ahead, used the same formula that it used here. Here, if I click on this, you can see the formula is exactly as before, except instead of using 1, or k equals 4, I'm using whatever is in this column, A, row 6. If I want to find the 100th term in the sequence, I can type 100, it will give it to me. If I type 1,000, it'll give me the 1,000th term in the sequence. Alright, so let's go back to the presentation. Alright, there are two very important types of sequences out there in the wild that we need to talk about. A geometric sequence is a sequence where the next term in the sequence is simply a constant multiple of the previous term. All of these sequences will follow a very nice formula. So if you recognize a sequence where every term is a multiple, the same multiple of the previous term, then you can quickly use the following formula to give you the equation for the sequence. So if the constant multiple is r, so if say I'm multiplying by 2 every time, r would be 2, and the starting term is a, whatever the sequence starts out at, then the sequence can be expressed in the following way. Either as a times r to the k, and that's where I'm starting out my sequence at k equals 0 and running up to infinity. This will be useful to start a sequence at someplace other than 1. And we'll see this in a later section. Here I'm starting the sequence at 0. So those a 0th term and then a first term and then a second term and so forth. Or I can use the formula a times r to the k minus 1. Here I'm starting my sequence out at 1, as we're used to from the rest of the sequence, and going from k equals 1 to infinity. So for example, a geometric sequence could be the following: 0.2, then 0.8, then 3.2, and then 12.8. Every term is simply 4 times the previous term. 0.2 times 4 is 0.8, 0.8 times 4 is 3.2, 3.2 times 4 is 12.8. So my r is 4, and my a is 0.2. Plugging those into either of these formulas will give you a formula for this sequence. So for instance, if I use this formula, it would be 0.2 times r to the k minus 1. And that's where k equals 1 is this term, k equals 2 is this term, k equals 3 is that term. If I use this formula, it would be 0.2 times r, which is 4 to the k, but this is the 0th term, so when you plug in k equals 0, you get this term. When you plug k equals 1 and you get this, when you plug in k equals 2, you get that, because this formula starts out where this is the 0th term, not the first term. An alternating sequence is any sequence that swaps back and forth between positives and negatives. So for instance, if you had a sequence like negative 1, 1 and going back and forth forever, that's an alternating sequence. These sequences will often involve a negative 1 to the k or some modification of that in their formula. So here are 5 examples. What I would like you to do now is to pause the video and take a few minutes and see if you can identify each of these 5 as geometric, alternating, both geometric and alternating, or neither geometric and alternating. If it's geometric or some modification of geometric, see if you can't figure out a formula for the sequence. So pause the video here and see if you can't derive formulas for each of these and identify the sequence type. Pause the video here and see if you can identify the sequence type, and again, if the sequence is geometric, identify a formula for that sequence. Alright, the first sequence is a geometric sequence because every time I'm simply multiplying by 3 to get the next term. 2 times 3 is 6, 6 times 3 is 18, 18 times 3 is 54. So here I'm multiplying by 3 each time, so the r is 3 in the geometric formula, and the starting point is 2, so my a is 2 in the formula. So my formula would be 2 times 3 to the k minus 1. Number 2 is an alternating. It's not a geometric because every time I'm not multiplying by the same value each time. 3 is actually a geometric. I'm multiplying by 1 every time. So if you plug that into the formula, you would get 7 times 1 to the k minus 1. But 1 to the k minus 1 is just 1, so you just get the formula 7, the constant sequence 7, as we discussed previously in the slides. Finally, number 4 is an alternating geometric. Every time we're multiplying by 2 to get the next terms, and we're alternating because it's swapping back and forth between negative 1 and positive 1. So to get the formula here, I'm going to include a negative 1 to the k. That's going to get a negative when k is 1, a positive when k is 2, a negative when k is 3, and so forth. The way you check your formula is to simply see if it's working. Plug in k equals 1. See do you get a negative. Plug in k equals 2. See if you get a positive answer, and so forth. Now what are we multiplying by each time? It looks like we're doubling. 1.5 times 2 is 3. 3 times 2 is 6. 6 times 2 is 12. This next number will be 24. In fact, negative 24 because of the alternating pattern. So I'm multiplying by 2 each time, so my r is 2. That gets me my 2 to the k minus 1. My starting value is 1.5. I just put 1.5, not negative 1.5, because I'm encoding the negative here, so I don't put the a as 1.5. I put the a as just 1.5. If you plug in k equals 1 into this formula, you should get the first number. When you plug in k equals 2, you should get the second term. When you plug in k equals 3, you should get the third term, and so forth. The exciting sequence 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 forever is neither alternating nor geometric. It should be pretty clear. I have an extra bit here at the bottom. This is looking at equation 4 but swapping the negatives. The negative, it doesn't start as negative and then becomes positive like it did in 4. That's swapped. So what I can do to fix that is change the exponent on the negative 1 here. I change it to k plus 1. So when k is 1, and I'm plugging in k equals 1 to get the first term, I'll get negative 1 squared, which is just positive 1. So I get a positive answer. When k is 2, though, I get negative 1 cubed, which is negative, and I get a negative answer. That will also work when I hit 3. I'll get negative 1 to the 4th, which will give me a positive. When k is 5, I'll get negative 1, when I plug in k equals 4, I'll get negative 1 to the 5, which is negative 1 to an odd power, which is negative 1, and I'll get a negative net answer. The rest of the formula stays the same. So, for dealing with these alternating signs, it's going to involve a negative 1 to some power. It involves some trial and error to see what should go in the exponent to make it work. There is not a fixed multiple of the previous number. Alright, transitioning to calculus. Back in Calculus 1, you studied about when does the limit as x goes to infinity of a function exist. You learned properties of limits, about the sum laws, the difference laws, the product laws of limits. You learned about L'Hopital's rule, limits of rational functions at infinity. You learned a lot about limits in Calc 1. You might want to go brush up if you're a little rusty on it. Since a sequence is an infinite list of numbers, a first number, second number, third number, fourth number, fifth number, forever, a very natural calculus question is, as I go further and further out in this sequence, as I go towards infinity in the sequence, am I getting really close to a fixed number? In other words, does the limit as k goes to infinity of a sub k exist? In which case, I would say that the sequence converges to that number. If the terms don't get close to anything, or the terms get really, really large towards positive infinity, so that the limit is infinity, or they get arbitrarily small going towards negative infinity, I would say it diverges to negative infinity. So some examples of sequences here. The first one, 1, 2, 3 forever, that is a sequence diverging to infinity. The terms are getting larger and larger and larger. The next sequence, 1, 1/2, 1/3, 1/4, etc. Those terms are getting smaller and smaller and smaller, and they're getting closer and closer and closer to 0. So I'd say that sequence is converging to 0. Sequence 3, the start of it's extremely weird. 10,000, some big number. Then all of a sudden it's 1, then a third, then a ninth, then a 1/27th. Looks like it's 1 over a power of 3 after that point. The beginning is weird, but the limit we're concerned with is at infinity, at the end of the sequence, or what we call the tail of the sequence, near infinity. Down there, near infinity, for large terms in the sequence, so like the 10th term, the 20th term, the millionth term, those seem to be getting really close to 0. So 3 is actually converging to 0. 4, I forgot my comma and ellipse at the end, so forgive me for that. It should be comma and 3 dots at the end. That is a sequence that's alternating, but as it alternates, they get really close to 0. It's 1, then negative 0.1, then 0.01, then negative 0.001. Even though we're bouncing back and forth between positive and negative, they're getting closer and closer to 0. So number 4, I would say, converges to 0. Hopefully, you can see that sequence 5 converges to 8. The terms in the sequence are getting closer and closer to 8. 6 is bouncing back and forth and doesn't appear to be getting close to anything. It's not getting towards infinity. It's not getting towards negative infinity. So I wouldn't say it diverges to infinity or negative infinity. I would just say number 6 plain old diverges. If we go back to the Excel spreadsheet that we made earlier, I would say this sequence is converging to 0 because for large K, my terms are getting really close to 0. In fact, if I plug a number even bigger in here, that's 10 times 1 times 10 to the negative 4. That's really close to 0. The terms are getting closer and closer and closer to 0. So the sequence converges to 0. Here's the mathematical definition of sequence convergence, and this just lights me up. A sequence A sub k converges to a finite number L as k goes to infinity, denoted by the limit notation, or simply as A sub k arrow L, read aloud as A sub k converges to L, if and only if for all epsilon greater than 0, there exists a whole number n, so that for all n, little n, greater than or equal to big N, we have that the absolute value of A sub n minus L is less than epsilon. Isn't that beautiful? Let's look at this a little bit closer. This is telling me how far apart AN and L is. And this is saying that it's smaller than epsilon. So what this definition is saying is that you challenge me with how close you need me to get to L. I'm not going to promise you I can get there. That's why I'm saying greater than L. So this is my error, how far away I am from L. But if you give me some error bound, like 0.1 or 0.001, or a tenth, or a billion, or 7, you give me some error challenge, how close you want the sequence to eventually get to L, then I can tell you how far to go out in the sequence. That's what this big N is. So that once I'm at that point and beyond, the distance that my terms are from L is smaller than the challenge you gave me. In even shorter words, for large K, A sub k is as close to L as we want, but it may not actually reach L. In other words, I'm not saying that epsilon can be 0. But if you want me to get really close to L, but not get there, the sequence eventually gets that close to L. Here are 2 examples. A sub k, 1 over k. This is the sequence 1 over 1, then 1 over 2, then 1 over 3, then 1 over 4, then 1 over 5. Those terms are getting really, really close to 0. If you look at this sequence, it's a weird formula, but if you plug in k equals 1 and work it out, then plug k equals 2 and work it out, and so forth. Say, look at it in an Excel spreadsheet. This would be a great time to actually open up Excel, try to code this like we did in the previous slide, and see, do the terms get closer and closer to a number? They will. They'll get really close to 1.5 or 3 halves. Don't stress, you won't actually have to apply this definition and go searching for a big N and applying the rigorous mathematical definition of sequence convergence. The reason is because if you look at this definition and compare it to the definition of limit convergence back in Calc 1, they're really, really similar. In fact, you can prove the following result. If a sub k is a sequence and f of x is a function where when you plug k into the function you simply get a sub k, then the limit as k goes to infinity of a sub k is simply the limit as x approaches infinity of the function. This is the Calc 1 business. In other words, you can treat sequences just like limits of functions. So all of your Calculus 1 results for limits at infinity will work for sequences. In other words, L'Hopital's rule will work, the standard algebraic manipulations you learned for solving limits will work, the end behavior of rational functions will work, etc. So as I mentioned before, you may want to go back to Calc 1 on limits, do some review before starting the homework and applying these calculus results to sequences. So I'll close with an example. So let's look a sub k be the sequence 3 times k cubed all divided by 4k cubed plus 1. If I want to apply my important theorem, I simply let f of x be that formula but replace all the k's with x. quickly notice, I don't even have to write this down, I'm just thinking in my head that if I plug in k into f, I get a sub k. So I'm just thinking about the sequence as a function instead of a enumerated list of values. Now thinking about it as a function. And now I take the limit as x approaches infinity of f of x. And I notice that this will be an indeterminate form. The top will be going to infinity. 3 times infinity cubed is infinity. 4 times infinity cubed plus 1 is still infinity. So it's an infinity over an infinity, which is an indeterminate form. That's not always 1. It can be a variety of different things. But L'Hopital's rule can come to the rescue and help me work that out. So if I apply L'Hopital's rule, which I'm doing at this step, I take the derivative of the top divided by the derivative of the bottom. The derivative of this is 9x squared. The derivative of this is 12x squared. L'Hopital's rule says that this is an indeterminate form of type infinity over infinity, or a 0 over 0. Then you can use this shortcut where you take the derivative of the top divided by the derivative of the bottom, calculate the same limit, and these two will equal. I simplify this because we know from Calc 1 that if you do algebraic manipulations away from this point that are valid, then the limit will be preserved. So I can cancel these x squareds, in other words, and I get 9/12, and the limits are equal. I can simplify this even further. It's 3/4, and we know from Calc 1 the limit of a constant is simply the constant. So I get the answer is 3/4. Go to Excel and try to figure out the first 10 and then maybe the 100th term and the 1000th term. See if they're getting close to 0.75 or 3/4. So again, a quick application of this major theorem we got and Calc 1 material, L'Hopital's rule. You can also use the end behavior of rational functions and the knowledge that back from Calc 1 that rational functions at infinity or negative infinity are controlled by the highest degree term and the leading coefficients. It's a very common shortcut in Calc 1. So if we apply that rule, since this is a rational function, I could just take the highest degree term and its coefficient from the top, the highest degree term and its coefficient from the bottom, simplifies to 3/4. The limit as x goes to infinity of a constant is just that constant. So again, I get 3/4. So an important note here is all of your limit laws from Calc 1 are back in play because of this major theorem we have. So as I mentioned 2 times before, it'd be a great idea to go review some of the basic limits from Calc 1. Alright, let's see another example of using calculus to find the limit of a sequence. Consider the sequence a sub k equal to cosine of k divided by k squared. So the first term of the sequence would be cosine of 1 divided by 1 squared, which simplifies to cosine of 1. The second term would be cosine of 2 divided by 2 squared, which is cosine of 2 divided by 4. The next term would be cosine of 3 divided by 9. The next one would be cosine of 4 divided by 16, and so forth. So we're wanting to know, do these numbers get closer and closer to a fixed value? Does this sequence converge? In order to see if this is happening, let's use Excel to see if that's actually what's happening. Are we getting closer and closer to a finite value? Opened up Excel in a new window. My first column is going to be my index for my sequence. The index is the variable used in the sequence. And then my second column is actually going to be my terms of my sequence. So say when I have k equals 1, I want to use the formula. This will be equal to cosine of this number. We're in calculus, so we want to do radian measure, so we need this to be cosine of 1 radian, but Excel defaults to radian measure for their trig functions. So cosine of 1 here, which is a2, will be cosine of 1, that will be cosine of 1 radian, divided by that number squared. So this is my k, my a2, hit enter, and it calculates the answer. If I want to find that for 2, 3, 4, and 5, I enter that in my k columns, and again I just click this and drag down, and it will populate my answers for each. So this is a sub 2, or cosine of 2 divided by 4. This is a sub 3, or cosine of 3 divided by 9. This is a sub 4, cosine of 4 divided by 16. This is cosine of 5 divided by 25, which is a sub 5. If I want to go further, I can put 10 Remember, Excel is pretty smart. It's going to auto-populate that knowing that I want to continue the formula. Cosine of 100 is 0 point, a bunch of zeros followed by this, something really close to what? 0. Every time I'm getting closer and closer to 0 as I go further and further down the sequence. So the terms, these, are getting closer and closer to, it appears, 0. So I think the limit exists, and I think the limit is 0. Let's go back to the presentation, and let's see if we can apply the calculus to figure out the limit and confirm via calculus that the limit is 0. To do this, let's bring our good old friend from Calc 1, the squeeze theorem, back. You may have called the squeeze theorem in Calc 1 the sandwich theorem. They're one and the same. Using our knowledge that cosine of x is always between -1 and 1 inclusive, we can actually find a nice bound on the terms of this sequence. What I mean here is that cosine is always between -1 and 1 on the y-axis. It never goes above 1, and it never goes below -1 on the y-axis. Because of this, I can multiply through this inequality by a positive number, and that's important. We'll need that in later sections. When you have an inequality, you can multiply it by a positive number, and it doesn't change the inequality. So I'm going to multiply this inequality through by 1 over x squared, which will be a positive number. This will give me that -1 over x squared is less than or equal to cosine of x divided by x squared, which is less than or equal to 1 over x squared. If I look at the limits as x goes to infinity of both of these, I know they're both 0. So the limit of the middle function must also be 0 by the squeeze theorem. So looking at my sequence, I have from the last slide that this is 0, and if I use my major theorem that we looked at a couple of slides back, this will then also tell us that a sub k converges to 0. So again, as a recap, we used Excel to see that this does appear to be converging, and we think it converges to 0. You can use Google Spreadsheets as well. You could also look at the graph of this where you replace x here and get an idea. It's going to be a whole lot harder to see using a graph because cosine alternates. It's a bit easier using Excel, but the cosine in the top makes me think that I might be able to use the squeeze theorem to figure out this limit. I do that by trapping it in between -1 and 1, because cosine is always between -1 and 1. Multiply that inequality by the positive number 1 over x squared. That gives me this inequality. Both of these limits are 0, so the squeeze theorem tells me that this is 0. The major theorem then tells me that this, if I plug in k here and think about it as a sequence, that sequence will go to 0 as well. So, to wrap up, what did we cover in this presentation? We were introduced to the concept of sequences. We learned about two major types of sequences, a geometric sequence and an alternating sequence. We learned how to look at a sequence and find the formula for that sequence, as well as if I give you a formula for the sequence, can you give me the terms of that sequence? And then finally at the end, using a major theorem, we learned that we can figure out convergence of sequences. We can do that by using the major theorem and applying Calc 1 results. We can also deduce that by looking at the terms, are they getting really, really close to a number? As we go further and farther out in the sequence, that can be done by inspection, by simply looking at the terms like we did on one slide. That can also be done by looking at Excel and looking at what are the terms getting really close to. Hopefully you took good notes on today's presentation. Again, remember to stay safe and healthy. That goes for you and your family members and everyone around you. I hope you have an amazing day.